Hey P2 kids, Mr. Canavan here. I'm going to run through your 0-point quiz for you from Unit 2, Constant Velocity. You worked on this yesterday. It's in your OneNote. This will be just me walking through the key. This key is also in your OneNote, but it might be nice to hear somebody talk through how they got some of the answers. Feel free to watch this more than once. Alright, so the first thing that the 0-point quiz has you do is to sketch velocity time graphs from position time graphs. Now remember, the position time graphs are showing where an object is over time, and the slope on a position time graph is equal to the velocity. So if we look closely, say, at this first one here, right? So this first graph, I'm going to switch colors so that we can see what I'm doing more clearly. Looks like I already used red. Okay, so for this first one, we'll notice that the whole time this object is moving away from us, right? Now, how can I tell that? Well, it starts at position 0, which would be right next to us, and it gets further away over time. Looks like after about 1 second, it's gone about 2 meters, right? After about 3 seconds, it's now 3 meters away, and after 5 seconds, it's 4 meters away, right? So we can read all of that off of there. What we want to be able to do, though, is we want to be able to calculate the slope and therefore plot it on the VT, or velocity time graph. So to calculate slope, remember you count up the rise over the run. So in this first portion here, it goes up 2 meters and over 1 second. So our rise is 2 meters. Our run is 1 second. That gives us a velocity of 2 meters per second for the first second. Right? The second part here goes up 1 and over 2, and then up 1 and over 2, right? So it's the same velocity, it's a straight line. So it goes up 1 meter for 2 seconds, which gives us a velocity of 0.5 meters per second, right? And that happens for 2 seconds. So that's what's plotted down here. So here's our 2 meters per second for 1 second, and here is our positive 0.5 meters per second, but that lasted for 2 seconds. That's how we got that. Okay? Now I realize I just misspoke and said it lasted for 2 seconds. Of course it lasts for 4 seconds because it starts at time 1 and goes time 5. So for 4 seconds. My apologies. The second graph here shows velocity as well, right? On our position time graph, we have some straight lines here, but we need to be careful because the object is not always going away from us. It looks like for the beginning part of it is. It's getting about 1 meter away from us every second. It does that for about 2 seconds, so its slope is 1 meter over 1 second, or 1 meter per second for the first 2 seconds, and that's what we're seeing down here. Okay? But then it takes this sharp change, right? And now it's actually was 4 meters away from us at time equals 2, but then by time equals 4, it's right back at us. So it went away initially, and now it's coming back at us. So in this case, its rise over run is it's going down 2 and then over 1, down 2 and over 1, which is why it's a -2 here. So it's going -2 meters every second, which gives us a velocity of -2 meters per second. And that goes on for 2 seconds, right? So hence this part here, 2 seconds at -2 meters per second. And that's how we get that graph. All right. Lots of practice for this, everybody. It's going to be 3 or 4 questions on the test, so make sure that you do those objective checks, that one that's on graphing. I think it's 2B if you want to have more practice with this. We also did a lot of practice worksheets, and there's a couple of videos on Actively Learn if you need more review with that. Okay? Now it's asking you here to just make a freehand sketch. So yours might not look exactly like mine, but it should be similar, because you need to be able to take like a written description, typed out description, and turn it into a graph. You may also have to be able to take a graph and kind of turn it into a written description or a typed out description. So both of these skills are necessary. So the first one says that an object moves away from 0 meters at a constant velocity. So we start at 0, it's moving away from us at a constant velocity, meaning this line is a straight line. And whatever this slope is, it's a positive number, it results in this velocity time graph on the right-hand side there. Notice how there's no numbers here, it's not really that important. This is a positive slope because it goes up and it goes over. Both are positive numbers, right? So we know the slope is going to be a positive velocity. Okay? Now for the second one here, it says an object that starts at a positive position, so it doesn't start at 0 meters, and moves towards 0 meters at a constant velocity for half the time, right? So I just judged half the time as being right about there. Then stops for the other half of the time. So if it's moving towards 0, then we look now, this is actually going to be our rise over our run. This is going to be a negative, right? That's going to give us a negative velocity, right? So whatever that number is, it's moving towards us for the first half. And then when it stops, that's when the slope equals 0 and the velocity equals 0, right? And so for the first half, we have a negative velocity. And then for the second half, our velocity equals 0. Okay, so that's how we decipher those, looking for important parts of the descriptors. All right, so there's our graphing. Oh my goodness, more graphs? Yes, I'm sorry, unfortunately. We do lots of graphing when we're trying to understand the motions of objects. So this first one says, what is happening at the intersection? Let's get familiar with the graph first. So the graph looks like we have a position versus time graph. We have two objects, one that's red, one that's blue, and it looks like they start at different places. The red object looks like 1 meter away from us, and the blue object looks like it starts 20 meters away from us. The red object gets further away over time, right? Remember that we're talking about when the slope is positive number. It has a positive velocity, whereas the the blue object is getting closer to us over time. So that's a negative slope and therefore a negative velocity. Okay, so what's happening where they cross? What's going on right here? Well, if you consider that this is the position at a given time, then it looks like at about 5.5 seconds, these two objects have the same position, about 9 meters away. What does that mean? If they're in the same place at the same time? Well, if they were on a train track, they would have collided with each other. But we're not going to say they're doing that. They're just basically passing each other. They have the same position at the same time. Which one of these, though, is moving faster, and how do we know? Well, I mean, we can calculate the slope, and we do that by determining the rise over the run. So in the case of the blue object, we'll start there, right? So the blue object goes down, looks like 1, 2, 3, 4 for every 1, 2 seconds. So it goes negative 4 meters for every 2 seconds, which gives us a slope of negative 2 meters per second. Okay, so it's moving 2 meters per second, but it's coming towards us, hence the negative number. Whereas the red object appears to be going up 1, 2, 3 meters for every 2 seconds. 1, 2, so it's going to be plus 3 meters for every 2 seconds. So that's be 3 meters for 2 seconds, which equals 1.5 meters per second. Okay? Now we can do that by looking at little segments here, or we could do it by looking at the whole length of the line, right? By looking at the total displacement. Either way, it's going to give us the same values, right? And since the blue one is going 2 meters per second, doesn't matter if it's going towards or away from us. This is asking what's moving faster, right? Then it is the blue one. It's got a steeper slope, and so it's got a greater displacement, greater delta x in 10 seconds. Okay, what does blue's negative slope mean about its velocity? Well, we just talked about that quite a bit. The slope of an xt graph is the velocity, and if the slope is negative, it's moving backwards or moving towards us. Okay, now writing a mathematical model. This can be quite a challenge. So let's just go back and remind ourselves that when we say a mathematical model of a line, we're talking about the slope-intercept form, right? So where y is the y value on the y-axis, m is the slope of the line, x is the x component on the x-axis, and b is where that line crosses the y-axis. So let's put our variables in here. So y is actually position. We've typically referred to it as x, right? And this is something that's in meters. And x, right, on the x-axis is time, which we use the symbol t, and that's typically in seconds. So if we substitute these in, then what we get is we get x equals m times t plus b. So all we need to do is for each of these lines is we need to figure out what m and b are, right? Well, we just did a little bit of that up there as I walked you through the graph. If we go for the red object, What is the slope of the red line? Well, we figured it out. It's right there, 1.5 meters per second. Okay, and where does the red line cross the y-axis? Right there at 1 meters. So then to write its equation, here it is. The position of the red object, right, x, is equal to 1.5 times t plus 1. Whereas for the blue object, right, again, we can do the same sort of scenario. We have the slope of the blue line is -2, and it crosses the y-axis at plus 20. So we get -2, the slope is here, crosses at 20, and so then we get x equals -2, the slope of that line, times t plus 20. All right, pretty challenging, but definitely doable. Okay. Next one, peregrine falcon. All right, peregrine falcon is the fastest of flying birds and is the fastest living creature. This falcon can fly 1.73 kilometers downward in 25 seconds. What's the average velocity of the falcon? So we've got some conversion factors here, but we need to start off by doing the equation, right? So our equation is that position equals velocity times time. So in this case, the distance that the peregrine falcon has traveled is 1.73 kilometers. It equals the velocity times the time. Well, it can travel 1.73 kilometers in 25 seconds. This is the equation that we set up right here. And we solve for v, and we get that the peregrine falcon is moving 0.0692 kilometers per second, which is a weird number. Let's put this into numbers we're more familiar with. We have to convert. So we need to convert those kilometers into meters. So we use this conversion factor here. 1,000 meters is equal to 1 kilometer. So basically, we put 1,000 meters over 1 kilometer, and we multiply it. Kilometers cancel, and we get that this is the same speed as that, right? It's just in a different unit. That's 69.2 meters per second. Wow, that's like, you know, most of a football field in a second. Okay, but how many miles per hour is that? So we take the same number here, and this time we're going to have to convert kilometers into miles, and then convert seconds into hours. So we figure that by multiplying this, there's a conversion factor here, right? This one, 1 kilometer is 6.2, or 0.62 miles, right? We get that the peregrine falcon is traveling 0.0429 miles per second. Okay, but how many miles per hour is that? So we multiply it by this conversion factor. We're going to turn those seconds into hours, right? So 60 seconds in 1 minute, 60 minutes, the same as 1 hour, and we find out that these three things are actually all equal. So this is equal to this, and this is equal to this. It's just in different units. Okay, that's a pretty fast falcon there, going 154 miles per hour. So, okay. And then we scroll down, and we've got this last bit of graphing here. And again, there's lots of practice with this on Actively Learn if you need to. In fact, you may have seen this graph already. So we're going to start by where is the object graphed above at time equals 6 seconds. So we go to 6 seconds, and we read up, and we get that it's located at 5 meters. How long did it take the object to travel 4 meters away? So we go over to 4 meters, and we look over, and we figure out it's 3 seconds. Was the object moving away, moving towards, or stationary at time equals 8 seconds? So again, we want to look at the slope here, and at time equals 8 seconds, it's flat, so it was stationary. What about at time equals 6 seconds? So at time equals 6 seconds, we have a negative slope, it's moving towards us. And what about time equals 3 seconds? At time equals 3 seconds, it's got a positive slope, so it's moving away from us. A qualitative description might look something like this. Not moving for the first 2 seconds, moving away for the next 2, stopping for 1 second, moving towards for 2 seconds, stopping for 2 seconds, and moving towards for 1 second. You can get detailed there if you want to. And then finally, drawing the VT graph from there. All of the calculations are here. Since I've only got about 30 seconds before this video has to be done, because we are using a free video recorder, I'm going to leave it there for you to be able to transfer the 0 meters per second for 2 seconds, +3 for 2, 0 for 1, -2 for 2, etc. right over to that graph. Nice work, everybody. Keep up your studying, and we will talk to you soon.